The topic for today is internal resistance. We've been treating each circuit element as ideal and separate. Batteries provide EMF, resistors have resistance, etc. But real batteries not only provide EMF, they also resist the flow of charge somewhat. In other words, the charge has to actually move through the battery and out, and there is some resistance to that flow of charge. These are not perfect conductors inside the battery. This is called internal resistance, and we usually denote it with a lowercase r rather than a capital R, partly because we want it to be small and we want that to remind us of that. We can conceive of it as a small resistor in series with the battery at the positive terminal. Now, some of the provided EMF is quote-unquote used up by the internal resistance. Since we can only attach probes outside the battery, we can never actually measure the EMF E, only the voltage across the battery terminals, delta V bat. To get a handle on R, we can connect an actual resistor, capital R, to the battery. The internal resistance and the actual resistor are in series, so the R equivalent is R, big R plus little r. This draws some current I according to the Kirchhoff loop law. We have current flowing like this, which is current flowing through the battery. And if we take this loop and we start here, we gain EMF and we lose the resistance because we've turned this circuit into now one of our ideal circuits. All told, we end up getting that the current is the actual EMF divided by the sum of the resistor I added plus the internal resistance of the battery. If the internal resistance is very, very small, if R is much, much less than big R, then the current would be the EMF over big R, as we would have found for an ideal battery, i.e., if the internal resistance is tiny, it looks like an ideal battery. But if R increases a lot, then the current falls. This is actually what happens towards the end of the life of a battery, where as the chemical reactions progress, if they're irreversible, they sort of build up gunk, and it becomes harder and harder to push current through, and so the internal resistance will shoot up, and that will drop the current. We can find the actual potential difference across the resistor by saying delta VR across our real resistor R is I times the big R, which will be E over the sum of the resistances times big R, or it will be some fraction of the EMF, the actual resistor over the actual resistor plus the internal resistance. And again, for negligible resistance, we see that it's just what we would expect. But for larger R, the usable potential decreases towards zero. Because this is also the potential we'd measure across the terminals of the battery. By the loop law, the amount gained, the amount we lose in the resistor has to be the amount we gain in the battery. We already had that the battery would have a voltage which is the EMF minus this loss to the internal resistance. So again, if we sort of think of our battery like this, then we have current flowing through it, and as we move here, we gain the EMF, but then we lose I times R. And this is where we're actually going to measure our voltage, so we'd have to combine both those effects. So delta V battery is the EMF minus the actual drawn current times the internal resistance. We end up calling this the terminal voltage of the battery because it's the result we get from a voltmeter across the physical terminals of the battery. Be careful here. Often in physics, terminal means the value you get to eventually, like the terminal speed and so on. That's not what we mean here. We're actually being very much more blunt. The battery has what are called terminals, and we've connected the voltmeter across them, and we measure the voltage between those terminals. It's not that interesting, but algebraically we can prove that the voltage across the terminals is going to turn out to be the voltage we had found before. And again, we see that the bigger the internal resistance R is, the lower the fraction of the EMF that we can access. All right, we can only access this thing. So if it's 1% or something like that, then it would be something like 1 over 1.1, which is like 99% of the EMF. But as R gets bigger, right, if the internal resistance ended up being equal to the actual resistance, then we would get only half the potential off the battery that we'd expect. Just a reminder. Students use a variable resistor, this is an example problem, to adjust the current in a circuit so as to measure the EMF and internal resistance of a battery. They get the data given below. Briefly, how can they use this data to find the EMF and the resistance R of the battery? Notice we don't use the internal resistance directly in the formula we have, and they don't give it to us. They just use the variable resistor to adjust the current flow. And they get this table out. How how can we find epsilon, find E and R? Of course, the simplest answer is if we were to make a graph of delta VB versus I, we see that we would expect, right, this is the formula we're saying connects the two. So if our variables are this on the horizontal and this on the vertical, then we expect a line to come out. So we'd have a line, and the slope of the line minus the slope is the internal resistance, and the intercept is the EMF. So for instance, here I had Dasmos plot that data, and we see that we do get a line, which is nice. And this is the equation of that line. So we get that the EMF is the intercept, and we get that minus the slope is the internal resistance. Different problem. Consider 4 identical resistors, each being 5 ohms, connected in parallel to a battery, as shown above. The current drawn from the battery turns out to be 4.6 amps, and we know the battery is a 6-volt cell, meaning it's supposed to put out 6 volts of EMF. Find the internal resistance of the battery in ohms. Well, the 4 resistors are going to have an equivalent resistance of 1.25. Why? Because 1 over the equivalent is 1 over 5 plus 1 over 5 plus 1 over 5 plus 1 over 5, which is 4 over 5. So the equivalent resistance is 5/4 of an ohm, or 1.25. And we also know that the actual EMF is I times the resistance in the circuit. But the resistance in the circuit is that 1 1/4 plus the unknown resistance. And then we just solve it. All right, then it's not particularly interesting. It's just some algebra. We get that the internal resistance is the EMF minus I times the equivalent of those 4 resistors divided by the current. And we find out that it's about 0.054 ohms.